So after I finished the last one, I kind of decided I should show you because I realized you're not going to get the exact same numbers, which is probably going to panic you, but the numbers actually give you the same location. So let me show you what I was talking about. In the X then, let's see, what do I have? My X center of mass is going to be, let's see, I'm going to have two of them. I'll write them out. I'm going to have X, mass 1 is this 1,200 kilograms times my 18 meters plus 1,200 kilograms times 18 meters divided by the total, the 3 times the 1,200 kilograms. There we go. And then you might look at this and be like, I don't feel like we're going to get the same answer. My 1200s are going to cancel out still. And what do I end up with? 18 times 2. So I get an X center of mass equals 2 times 18 divided by 3. And then you're going to look at that and be like, that is not the same as 6. 18 divided by 3 is not the same as 18 divided by 3 times 2, but you are absolutely correct. But let's think about where we've defined our center or our origin from. So this whole entire length here is 18. When I said that I'm calling this location 0, I came out here 6 meters. So what does that mean I have left? That means I have 12 meters left. So when I define my origin with this really bad shaded in green line, I am coming 12 meters out is the math. So it's telling me again, come out here. Now for my axes in the Y, I look at that and I still have just the 1. So once again, it's just going to be up 6. So it is identical. I wanted to show you that because that is one thing that crossed my mind when I was kind of hesitating hitting stop on the last video, is that depending on where you define your axes is where your answer will live or mathematically look like. In other words, this one has an answer of 6, 6. This one here has an answer of 12, 6 as far as coordinates go. So if you talk to your classmates, the moral of the story I'm trying to get to, if you talk to your classmates and you're like, I got 6, 6, what did you get? And they got 12, 6, and then you panic, and then you all think you're doing something wrong, draw a picture of it and make sure that you're comparing apples to apples, so you don't talk yourselves into thinking you don't have it. Okay, so I promised you the integration on this, and this is going, if you look in your textbook, this is if we take something like this. I actually had to work for any of them, but doing the integration just kind of feels a little bit silly when it's just like 3 masses. So what do we got? This is going to be like an evenly distributed mass, and in this case I chose something that's like a board. And so I have, this is going back to where I was drawing like my little lines. We're going to sum it up, which means I'm taking slices. So just like electrostatics, when we were taking like slices of the surfaces that we were looking at, looking for each charge and how it was distributed along, we're doing the same thing. We're looking for our change in mass over some distance away. And so we are integrating with respect to the mass, which might feel a little bit weird. But if you look in your book, what has it done? It's done this thing in terms of the H. So it's done some sort of substitution. And what it said is that we can go like this. We can go, I have this change in mass per total mass is going to give me this relationship of the change in distance, or the change in L, the length, over the total length. And so what you see is then that they write it in the book, and they go, so my change in mass, and I can move the capital M up here. Excuse me. Sorry about that. So we can rewrite this to where we have then our change in mass equals my mass divided by my length. And I was just looking at your book. Your book does it as mass divided by length, but it uses dx for the change in distance. So let me be consistent with what your book says. We have this thing. And now the dog's going to start barking, because that's what they always do for me. So if I come here and I say, okay, for my x center of mass, what am I looking at? I'm looking at this integral from 0 to the total mass times the little distance away that it is times dm. And if I define dm in terms of dx, so something that's actually integrable for me, so I can have like this defined amount of something, then I can go, let's see, oops, I forgot my 1 over m. 1 over m. So I get 1 over m. We keep consistent, capital M, there's the magic E. Integral from 0 to, we're going to change our limits of integration. So it'll be 0 to L, the total length, instead of the total mass. And let's see, I'm going to have my x times, now I'm making my dm substitution of m over L dx. And then I can clean this up even more. I can go x center of mass equals my m's cancel. My 1 over L can come out because it's constant. It's just the total length of whatever it is I'm looking at. And then 0 to the total length, x dx. And then furthermore, I get that x then is this 1 over L times x squared over 2 times, or evaluated from 0 to L. There we go. Why I'm going uphill with my writing, I don't know. And so what does this give us? Well, on this evenly distributed mass, surprise, surprise, you can kind of look at this and you'll be like, okay, what am I going to get? I'm going to get L squared over 2. So let's write this out. Get L squared over 2 times, just putting the L into the x, times 1 over L. Well, this gives me what? 1/2, or L over 2. 1/2 of the total length. So if I have something that's evenly distributed, it is going to spin easiest about the center of its evenly distributed mass. So you can think of that in terms of, you've probably seen that if you try to pick up anything heavy, right? How hard is it for you, and that's going to come into the inertia, our next topic, how hard is it to pick something up like a 2x4, an 18-foot 2x4? Do you want to pick that up at the very end and carry 18 feet of a board in front of you, like trying to feeder it like that? Or do you want to just like pick it up in the middle? It's where you have this nice balanced mass on both sides. That's what you're doing. You're picking it up by its center of mass. So you have now secured it. Now it's going to be easier to rotate about that center of mass, but by golly, you put your hand right where it's easiest to carry it too. Interesting. Now, as far as other mass distributions go, we're going to talk about that more in terms of inertia here in just a bit.